Before you view this presentation, please be sure that you look at the basics of covalent bonding video lecture that should be somewhere near this one. Otherwise, it might be a little bit on the confusing side, but once you view that, uh, things like this are going to start to make a little bit more sense. Here's an example of where nitrogen and hydrogen come together in a molecule that is covalently bonded. And you'll notice that some of these lines that we saw in the very first presentation are right there. The two representations of the Lewis structure look like that. And another thing to remember is that each time you draw a line, it actually means that you're sharing two electrons. There is carbon dioxide, the two different ways that you can look at carbon dioxide, and it also shows you the various parents' Lewis structures and how they all come together to ultimately form this compound that has all of its octets filled. To look at this slide, it is kind of an introduction to the basics of organic chemistry being the chemistry of carbon chains and such. You can see some of the things that can start to happen is that you can kind of build bigger and bigger and bigger molecules just by kind of stringing together carbons. Sometimes carbons, oxygens, and carbons, sometimes carbons and nitrogens and carbons, and sometimes both. But this is going to be something that we're going to be talking a little bit more about once we get to organic chemistry, which I think happens the very last week. But what we're going to be mostly talking about in this presentation is just like a real brief introduction to something called molecular geometry. All of you that have taken like a math course in geometry know all the fun, so you know a little bit about what to expect. But the whole idea is that if you have a Lewis structure of a covalent molecule, each molecule has a particular shape. Each time you've got an atom in the center of two or more atoms, they tend to have particular shapes. And the full picture, if we were going to talk about all the possible shapes, this is going to be included as a resource guide. But the good news about this resource guide, it looks pretty complex, especially once you get down to geometries that bond to 5 or 6 different things. But luckily in this class, that doesn't really describe too much anything we care about. So we're really only going to be talking about geometries based on linear, trigonal, planar, and tetrahedral geometries. So what you're essentially going to be doing, and this is going to be the source of the very next little video lecture. I'll kind of take you through exactly what's going on in this animation, and hopefully you'll understand this particular slide a little bit better. So this is called VSEPR theory, which is valence shell electron pair repulsion theory, but that never made much sense to me. So what I call it is electron clouds try to stay the hell away from each other theory. So every single one of these shapes is going to be dictated by what's called the number of electron clouds. And there's going to be different things that count as an electron cloud. For instance, a bond counts as an electron cloud. A double bond might count as one electron cloud, right? And so even though it's a double bond and it's got 4 electrons, they're all kind of doing the same job, so they're considered its own kind of electron cloud. Triple bonds also count as electron clouds. And the one last cloud that really is probably going to become the most important in terms of us determining actual molecular geometries and choosing from these geometries right here has to do with what's called a lone pair of electrons. It turns out that oftentimes on atoms, there are electrons that are just kind of situated on the atom and they're not necessarily doing anything other than filling the octet. So we call those lone pairs of electrons, and you'll kind of see what they look like. This one actually, you can see the lone pair of electron there hanging out on that little red atom right there. And so it turns out that what these lone electron pairs do is they do affect the geometry, but you really don't see them. So for instance, you can see that this guy is bent, right? And it is bent because it's almost like that kind of invisible lone pair of electrons right there is pushing these other 2 bonds away from it. Same kind of thing is happening in this geometry, right? This guy is really looking like a tetrahedral geometry, right? Which we'll talk about in a lot more detail in just a second. And you kind of lopped off one of the atoms and put this invisible lone pair there. So what it looks like is this little pyramid. And once we start kind of rotating these around, you'll actually see where the heck all these different shapes come from. So go check out that very next lecture.